All right, today we're diving into one of the biggest shakeups in artificial intelligence, vision transformers. We're talking about how a technology that was originally built for understanding language completely flipped the script on how machines see and make sense of our visual world. You know, for decades, computer vision had a clear champion. There was a go-to method for pretty much everything, from telling cats from dogs to powering self-driving cars. But then, an idea from a totally different field, from models designed to understand sentences, came along and just rewrote all the rules. Okay, so to really get what happened here, you have to think of it like a classic story. You've got the long-reigning champion on one side, and then this unexpected new challenger that came straight out of the world of text. So on one hand, you've got convolutional neural networks, or CNNs. The best way to think about these is like a detective with a magnifying glass. It scans an image piece by piece, looking for small local clues, an edge here, a specific texture there. But on the other hand, you have the transformer. Now, this was born from language models, and its superpower is context. It doesn't just look at one word at a time. It looks at every single word in a sentence all at once to figure out the real meaning. And that leads to the big kind of mind-bending question, right? How on earth do you take a model that's a genius with grammar and sentences and teach it to understand a photograph of a dog or a car or a sunset? Well, the solution turned out to be surprisingly elegant. The breakthrough, the absolute genius of it, was that researchers didn't try to teach the transformer a new trick. Instead, they just completely reframed the problem. They figured out how to show the image to the transformer in a language it could already understand. And this quote, man, it just perfectly sums up the big idea. It's the actual title from that groundbreaking 2020 paper. The whole concept was to treat an image not as one big, complicated thing, but as a collection of smaller pieces, like a sentence that's just made of visual words. And honestly, the idea is way simpler than you might think. You literally just take a picture and chop it up into a grid of little fixed-size squares or patches. And just like that, you've turned a complex visual scene into a simple, straight line of items. And that is exactly the kind of data a transformer is built to handle. So here's how it actually works, broken down into 4 simple steps. First, you split the image into all those little patches. Second, you flatten them out into one long sequence. Third, and this is so important, you add positional information. You give each patch a little tag that says, hey, I came from the top left corner, or I'm from the bottom right. Without that, it's just a meaningless jumble of squares. And finally, you feed that whole sequence into the transformer. Now, the magic behind all of this is a mechanism called self-attention. What it does is it lets the model look at one patch, say one containing a dog's ear, and figure out how important it is in relation to the patch with the nose, and the one with the tail, and, well, every other patch in the image, all at the same time. And that's its superpower. It's not just seeing isolated details. It's building this big, holistic, global understanding of how everything in the image connects. But you know, that first paper back in 2020? That wasn't the finish line. Nope, that was the starting gun for an absolute explosion of innovation. The first vision transformer, or ViT, quickly gave rise to a whole family of even better and smarter models. I mean, just look at how fast things moved. In 2020, the original ViT shows up and proves it can go toe-to-toe with the best CNNs. Then, just 2 years later, the masked autoencoder, or MAE, brings in a totally revolutionary way to train these things. And by 2024, you've got models like Dino V2 that are learning these incredibly rich visual concepts without needing a single human-provided label. It's just wild. And the idea behind these masked autoencoders is just, it's so clever. You basically play peekaboo with the AI. You show it an image, but you randomly hide like 75% of it. And then you just tell the model, okay, fill in the blanks. By forcing it to reconstruct the missing pieces, it has to learn this really deep, almost intuitive understanding of what objects and scenes are supposed to look like. This self-supervised approach was a total game changer. Why? Because suddenly, you didn't need teams of people to sit there and manually label millions of images, which cost a ton of time and money. Now, these models could just teach themselves to see by learning from the billions of unlabeled images all over the internet. It unlocked a whole new level of scale and capability. Okay, so we've covered what they are and how they got here, but what's the big deal? Like, why should you really care about all this? Let's get into the real-world impact. All right, let's put these 2 approaches head-to-head. CNNs are fantastic at focusing on local details, and they're pretty efficient, especially with smaller data sets.
ViTs, on the other hand, are all about the big picture, the global context. Now, there's a trade-off for sure. ViTs are data hungry. They need a ton of it to get going. But once they do, their potential, their capacity to learn is just higher. And that global view makes them tougher, more robust to things like image distortions, or if an object is partially blocked. They're just two fundamentally different ways of seeing.
And this ability to see the whole picture isn't just academic. It has opened the door to some incredible new applications. For self-driving cars, it means understanding a whole chaotic intersection, not just the car right in front. In medicine, it's about spotting tiny, subtle patterns in a chest X-ray that a person might miss. It's even being used for advanced weather prediction because it can see massive, large-scale patterns, and it's the engine behind all these amazing AI image generation tools. In almost every case, seeing the bigger context is the key.
And the scale we're talking about here is just mind-blowing. To put this into perspective, a vision transformer built this year in 2024, specifically for weather and climate prediction, has 113 billion parameters. That's a level of complexity and raw power that would have sounded like pure science fiction just a handful of years ago. And we're using it to try and solve some of the biggest challenges we face. So, we'll end with this thought. We've basically moved from an AI that sees the world through a keyhole to one that can take in the entire horizon at once. As this holistic, context-aware way of seeing becomes the new standard, the real question isn't just about what problems we're going to solve. It's about what new things we're going to be able to see for the very first time.